Hello, my name is Pierre Kervella, and I am an astronomer at the Paris Observatory, where I study the working of stars. Stars are responsible for almost all light that we see. Almost all natural light, day and night, including the light from the moon and planets, comes from the sun, our star. There are a lot of stars, approximately 100 billion just in our own galaxy, the Milky Way, and we think that there are more than 100 billion galaxies in the universe. Stars are responsible for chemistry. Hydrogen, helium, and a small amount of lithium were formed during the Big Bang. With only hydrogen and helium available, complex molecules cannot form. The production of heavy atoms, critical to form complex molecules, is only possible inside stars. Due to thermonuclear reactions in their centers, stars form new atoms, increasing the chemical complexity of the universe and producing light. Without stars, planets could not have been formed, neither could water or living organisms. This evolution is irreversible. A star is essentially a very simple physical system, a ball of gas emitting light because it is hot. In this gas, atomic nuclei and electrons are separated, forming what we call a plasma. The atoms are at very high temperatures and thus emit photons that we observe. The gas in a star is in equilibrium thanks to two opposing forces. Pressure that works to make the star expand, and gravity that makes it contract. These two forces balance each other, and, for example, in the case of the Sun, they define its almost perfect spherical shape. A star continuously loses energy and cools by the radiation it emits. A source of heating is thus needed to preserve this balance in the long term. This source is at the center of the star. It precisely and continuously compensates energy losses by radiation. The fundamental physical properties of a star are its mass, radius, luminosity, and temperature. The mass is the main parameter determining the evolution of the star. The surface temperature is responsible for its color. Hotter means more blue, and colder means more red. The Sun, with a medium temperature of 5,800 Kelvin, is mainly yellow. Betelgeuse, much colder with 3,600 Kelvin, is clearly glowing orange in a winter sky in the northern hemisphere. Rigel, also from the Orion constellation, is blue instead, its temperature being around 11,000 Kelvin. In normal conditions, the atom's nuclei repel each other, never colliding between themselves. At the center of a star, temperature can reach millions of degrees and the pressure is huge. In these extreme conditions, atomic nuclei can collide, triggering nuclear reactions. We talk of nuclear fusion because in most stars, 4 hydrogen nuclei with a proton each will combine to form a helium nucleus with 2 protons. The helium nucleus that forms in this process is slightly lighter than the sum of the masses of the 4 hydrogen nuclei. This mass difference converts into radiation in the form of a high-energy gamma-ray photon. A small mass fraction is thus transformed in radiation. The gamma-ray photons heat the gas in the center of the star, maintaining pressure and balancing gravity, which tends to contract the star. The energy produced at the center is transported to the surface and emitted outwards to space in the form of light. The ratio of nuclear reactions at the center balance precisely the energy lost by radiation. For example, to produce the current radiation emitted by the Sun, 600 million tons of hydrogen must be burned per second. The mass being converted into light is more than 4 million tons per second. There is, however, a minimal mass needed to trigger nuclear fusion in a star. If the mass of the gas is not enough, pressure will not be high enough at the center. Under a certain mass, the star will not start burning hydrogen into helium. This critical mass is approximately 8% of the solar mass. Almost everything in the universe is rotating: planets, stars, gas clouds, and galaxies. The main reason for this is that there is conservation of the angular momentum in a physical transformation in an isolated system. For example, an interstellar cloud will transmit its angular momentum to the star being formed and to its planets. This is why almost every planet in the solar system rotates around the Sun in the same direction. The planets also rotate around their own axis in the same direction as the Sun. The rotation of the Sun around its own axis takes more or less a month, but there are stars that rotate at a much higher rate. Since a star is a ball of gas and not a solid object, a high-velocity rotation deforms it in a flat ellipsoid. Even the nearest stars are too small in the sky to allow measurements using a classical telescope. The star with the biggest size on the sky is Betelgeuse, its size being comparable to the size of a human being in New York when observed from Paris. The advancement of observational techniques enables us to study the surface of near stars. For that, we combine several telescopes in a technique named interferometry. Recent observations from interferometers, such as the VLTI, the Very Large Telescope Interferometer, and SHARA, the Center for High Angular Resolution Astronomy, have allowed us to measure the shape of fast-rotating stars: Altair, Achernar, Vega, Regulus, and Alderaan. Fast-rotating stars are not rare objects. In fact, many of the stars we see in the sky with the naked eye are ellipsoids and not spheres. A good example is the Pleiades, or the Seven Sisters. I study these fast-rotating stars. I measure their deformation by means of interferometry and how light is distributed at their surfaces. Thanks to these measurements, one can build numerical models of these stars that help to better understand the distribution and dissipation of the angular momentum. I am particularly interested in a star in the southern hemisphere, Achernar. It is 10 times bigger than the Sun and rotates around its axis in only 2 days, comparing to the Sun, which takes 1 month to complete one rotation. Its equator rotates at more than 250 kilometers per second, and its equatorial diameter is bigger than its polar diameter by a factor of 1.5. A star is not eternal. It has a beginning, an evolution, and an end. As we saw before, for a star to shine, nuclear fusion must be triggered at its core. For that, it has to possess at least 8% of the solar mass. If it has a mass lower than this value, we will have a brown dwarf or a planet like, for instance, Jupiter. A star is formed from a huge gas cloud called a molecular cloud, where hydrogen atoms exist in molecular form, H2. These molecular clouds can have several thousand times the mass of the Sun. Due to the gravitational force created by its own mass and to an external perturbation, a molecular cloud will collapse and contract, its matter forming protostars of different masses. If we put the stars in a graph plotting color versus luminosity, almost all stars will fall in a diagonal called the main sequence. Once nuclear fusion reactions are triggered in its center, the star is in the main sequence. It is the longest stage of its life. For the Sun, it will last around 10 billion years, and at the moment the Sun has already lived half of that. When all the hydrogen in the center is consumed, the star will start burning the helium core. However, this reaction requires much higher pressure and temperature. So, the star will change its structure. It grows due to the higher pressure. Its surface will become cooler, and the star will become a red giant. The lifetime of a star depends on its mass. A star with less than half the solar mass will burn a small amount of nuclear fuel, thus glowing faintly for tens of billions of years. A star with a mass several tens of times that of the Sun will burn lots of hydrogen and will thus glow brightly, but just for a few million years at the most. It is interesting to notice that small stars live for a very long time, several tens of billion years. The smallest ones even seem to be eternal. We know some stars that are almost the same age as the universe, like this faint star in the Lion constellation. Once the nuclear fuel is consumed, the star can no longer maintain a high enough pressure to balance its own gravity. Depending on its mass, this fact will have different consequences. For small and medium stars, the end will be peaceful enough. They will disappear in space, leaving behind their inert core as a remnant called a white dwarf. A typical white dwarf has a size comparable to the Earth, and a huge density of around a ton per cubic centimeter. Stars with a mass 10 times higher than the solar mass will end quite violently. Nuclear fusion will stop quite abruptly, depriving them of the necessary pressure to balance gravity. As a result, the internal layers will collapse onto the core in just a few seconds. When this implosion happens, the impact of the matter falling onto the nucleus triggers very violent nuclear reactions, leading to the star's explosion. It is what we call a supernova. In the implosion stage, the star core suffers such a high pressure that the atomic nuclei coalesce completely, forming a quite unique celestial object composed of neutrons. It is what we call a neutron star. We call it a neutron star, but in fact it is everything but a star, since there are no nuclear reactions occurring. The densities of these objects defy imagination, being around 100 million tons per cubic centimeter. For the most extreme cases, stars with more than 30 solar masses, pressure is so high at the time of supernova that not even neutrons can resist. Matter will collapse completely onto itself, forming a black hole, an object from which not even light can escape. After its death, the matter the star was composed of is thrown into the surrounding space. Peacefully or violently, atoms that were transformed by nuclear fusion, now heavier and more complex in terms of chemistry, are given back to the interstellar medium. The next generation of stars will be formed from this new matter. The presence of heavy elements like oxygen, carbon or silicon will enable the formation of water molecules, organic chemistry and terrestrial planets. It is through this recycling of matter that stars help evolve the chemical diversity of the universe, from the hydrogen and helium at the Big Bang to complex molecules.